Welcome back to another How to Calculate video. My name is Dustin Backey, and in this video we're going to be going through Angular Kinematic equations, and we have a number of those, and so we're going to go through a few different examples and try to work our way through each of those different equations. Alright, grab a calculator, some scratch paper, and let's get after it.
Okay, we're going to go through a few Angular Kinematic examples looking at how we would calculate some of our basic Angular variables, such as displacement, velocity, acceleration, tangential velocity, those sort of things. And so we're just going to go through a few different ones, kind of in rapid fire sort of order. So the first one we're going to look at is a displacement question. And essentially what is going on here is, let's go ahead and set this up. Let's look at someone who's going to be doing some knee flexion. So here they are at full extension. This is their lower leg, and let's say this angle right here is 178 degrees. And let's say they go to here. So almost 90, maybe a little less. Let's say this is 82 degrees. So we have some knee flexion going on here, and what we want to do with angular displacement, so let's just establish that if we are trying to find angular displacement, we want to take theta final minus theta initial, right? Angular displacement, we use the Greek letter theta here, and we take theta final, or angle final, minus angle initial. And our final angle is 82, and our initial angle is 178. And we need to remember with angular displacement that it's the absolute value here. So we want to put our absolute value signs there. And what we end up getting here is 96 degrees. It would have come out negative, but because we are using the absolute value, we want to use simply that distance away from zero, that is the 96 degrees. Oftentimes we'll go to radians, and if we remember right, there are 57.3 degrees in 1 rad. And so if we take this 96 and divide it by that 57.3, what we get is 1.68 rads. So we have two potential answers here for this one, 96 degrees or 1.68 rads. All right, let's go ahead and dive to another one. All right, so let's look at some angular velocity calculations. So let's figure out angular velocity. And the example in this case is going to be a ice skater jumping up and doing 3 full twists in the air. So they're going to, let's see if I can draw an ice skater. There's a skater. There we go. Great ice skater. They are going to jump, and they're going to do 1 full rotation, another full rotation, and a third full rotation before landing back on the ice. So they're doing 3 full rotations, and we know that each of those full rotations is 360 degrees. Okay, and let's say this time was, let's just say 0.8 seconds. That's how long she was in the air. So we want to find out how fast this ice skater was spinning. And so we represent angular velocity with the Greek letter omega, and it is that change in theta over the time. And in this case, we know the total displacement that this person did, or this ice skater did, is those three 360s all added up together. And so what we get is we get the angular displacement of 1080 degrees, and we divide it by the 0.8 seconds. And when we do this, we get 1,350 degrees per second. And so let's say we were going to be doing this in radians. We would need to convert the degrees to radians. And so we have 1,080 degrees divided by the 57.3 is going to equal 18.85 radians. And so if we go ahead and go down here and replace our degrees with radians, we'll find out what this is in radians. And so we will have the 18.85 rads divided by seconds. We are going to get 23.6 rads per second. So an example there of calculating angular velocity using that omega. Typically what happens is we use this omega here, or whenever you see omega, you want to think rads per second. But some questions and problems will call for degrees, and that's typically fine. It's as we move into other equations where omega is part of it, we are going to assume that it's in rads. And so we'll see examples of that in a minute. Let's go ahead and jump to another question. All right, for this one, let's look at angular acceleration. And what we're going to imagine here is a discus thrower. And I'm terrible at drawing, so I'm not going to do a very good job of this, but we have a discus thrower here. He's got the discus there on his shoulder, and he's going to start spinning around to throw that discus out, right? So he's going to spin, throw that discus out. And let's say his starting angular velocity, so omega starting, is 5 rads per second. And let's say his omega final, so we'll say that's the initial, omega final is going to be 25 rads per second. So he has increased his angular velocity, and therefore we quantify that with the angular acceleration. And we use alpha in order to find angular acceleration, or to represent that, and it is the change in omega over time. So let's say the time was, let's just say for ease, 1 second is how long it took him to throw this discus. And so let's go ahead and do that. We need the final minus the initial, and so that's 25 minus 5 from each of those, and the time of 1, and so we are left with 20 rads per second over 1 second, and we get 20 rads per second squared for our answer. So this is really similar to linear acceleration as well, right? We are taking the change in velocity and looking at the rate that it's happening under. So fairly straightforward there. Let's go ahead and do another equation here. Okay, for this equation, let's go ahead and find the tangential velocity. And when we look at tangential velocity, we want to basically look at the linear speed of a point of an on something in angular motion. And so let's say for this one we have a hammer thrower spinning around, and we want to know how fast the tangential velocity of the hammerhead is, how quickly it is. Let's say he is spinning and omega is 1200 degrees per second, and the radius of the hammerhead from the axis of rotation is 1.2 meters. And for this, tangential velocity is simply omega times radius. And so when we do this, we want omega to be in rads. So let's go ahead and convert that to rads by dividing it by 57.3. So when we convert the 1200 degrees per second to rads, we get 20.94 rads per second. So let's go ahead and calculate this. VT, sorry, I keep doing VI. VT equals 20.94 times the 1.2, and we get 25.13 meters per second is how quickly the head of the hammer is moving. So we went through our main variables here, right? We did angular displacement, we did angular velocity, we did angular acceleration, and we looked at angular velocity to linear velocity here with tangential velocity. So hopefully those different problems help you see how to use each one of these in a bit more of an application, or from a bit more of an application standpoint. We'll catch you in the next video.
Alright, thank you all for watching. Hopefully you know a bit more about biomechanics after that short video. I want to take a moment and just encourage you to subscribe to the channel to stay up to date on all these videos as they get posted, but the subscription also actually helps me out as well. So help support me, help stay up to date, hit that subscribe button. But I also want to take a moment and point out the two textbooks that you're seeing references to throughout this series. The first one is Fundamentals of Biomechanics by Dwayne Knudsen, 2nd edition, and that book is available online completely for free as a digital copy. Just do a little bit of Googling with the name there and the author and you'll be able to find it. The other book that we're using as a main reference is Biomechanics of Sports and Exercise by Peter McGinnis. And so I encourage you to try to find that one a bit as well. I don't think I have a free version for you available, but it's out there. It's reasonably affordable as far as textbooks go. But I encourage you to look more into those if you want a deeper breadth of topic and more discussion on the topics we cover in these videos. Thanks for watching. We'll catch you next time.